Okay, this is FRQ 6, the 3 15-minute ones for a total of 45 minutes. As I've done with all the videos, I am going to walk through these, show you where the points were, walk through my thought process on them, and then as always, if you have questions on anything, please feel free to send me an email, snap a picture of your work if you're having trouble grading it, whatever the case may be. Grading, obviously, I think will be the one that's potentially the trickiest for some of us because of the partial credit element we've discussed many times, which is if you have made a mistake early on in the problem that somehow adversely affects some of the remaining steps, you could still get points following your mistake if your work is accurate reflecting your mistake. Recognizing, of course, that your work now is going to look very different than mine because you've made a mistake, and so your work's going to look different, right? That doesn't necessarily mean you lose all of your points unless you have oversimplified the problem. And therein lies the rub for most of us as we are grading. If you're looking at it going, I don't know if I oversimplified this, take a picture, send it my way. I'm more than happy to say, yes, you'd get 2 out of 3 points or 3 out of 4 points or whatever the case may be. I'm here to support you if that would be helpful. Okay? So here we go. This one came out of 2019. It was a non-calculator one. We had parts A, B, and C. A was worth 4 points, B was worth 2 points, C was worth 3 points. And if you wanted my recommendation taking a look at this, I think part C is actually the easiest part of this particular one. Then part A comes in a close second. Aspects of part A are not easy, but aspects of it are maybe a little bit more straightforward. And then part B, I think, is the weirdest one, which again, you might differ from my assessment of it. But if I were doing this one, I'd do C, A, and then B. Of course, in my video, I'm going to walk through this as A, B, and C, just so you can see where your points are, and so on and so forth. Okay. We have a region R enclosed by the graph of g of x and h of x, the y-axis, and the vertical line x equals 2, as shown in the figure above. Now, this was a non-calculator one this particular year, so you would have been required to know which of these functions was which graph on your own. And I don't know about you, I have no idea what negative 2 plus 3 cosine pi over 2x looks like between 0 and 2. Or for that matter, what 6 minus 2 times x minus 1 quantity squared looks like between 0 and 2. What I do know is this. I can plug numbers into both of those functions. So if you wanted my recommendation, I'd plug 0 in, because one of these functions, when I plug in 0, I'm going to get 1, and one of these functions, I'm going to get 4. And I'd pick whichever function's the easiest for you to plug into, which for most of us probably is h of x. I know not everyone's super comfortable with that trig. Okay, and so if you were to plug 0 in here, h of 0 equals 6 minus 2 times 0 minus 1 squared, which is 6 minus 2, or 4 up here. So that tells me this is my h of x function, and this is my g of x. And if you wanted to check that, you could plug 0 into g of x, and you'd get 1, confirming that g of x is the lower function. Okay, so part A, find the area of R. This comes out of 6.1. Area is, well, can be expressed in terms of y, but that never has to be expressed in terms of y. So we're going to leave it in terms of x. So my x bounds are 0 to 2. And then it's upper minus lower. My upper is the h of x function. My lower is the g of x function. So we're doing the h of x function minus the g of x function. Now careful with this minus g of x. You have two choices. One, you can put parentheses around g of x as you put this in because it's behind the minus. You would have to do that unless, 2, you choose to distribute the minus into your g of x as you rewrite this. So minus times the negative 2 would be positive 2. Minus times the 3 would be minus 3. Okay? And then we are integrating this, taking the integral of this function. Integral of 6 is 6x. Back here you have a couple of options. One, you can leave it as is because this interior has a du of 1. If we were to do u-du substitution, you don't actually have to worry about the chain rule. And so you could add 1 to the exponent, so x minus 1 cubed, and divide by the new exponent, and you could call it good. Or 2, you could do you could FOIL this, right? X squared minus 2x plus 1. and distribute the -2 in, and then just do power rule on all of those different pieces. It's a pretty easy FOIL, and so you might like that method instead. Integral of 2 is 2x. And then back here, we do have a u to u substitution, so I'll go ahead and show that in red up top here. U is pi over 2x, du would then be pi over 2 dx, which I don't have a pi over 2, so I'd be dividing that to the other side. And that 2 over pi would need to make its way into my work with the 3. Integral of cosine is sine. That last piece, I think, is especially challenging part of part A, with that u to u substitution element. Okay, and then your answer, which is plugging in your upper minus plugging in your lower. So plugging in our 2, we get 6 times 2, which is 12, minus 2/3 times 2 minus 1 cubed, plus 2 times 2, which is 4, minus 6 over pi, sine of pi over 2 times 2, which is pi, minus plugging in your lower, 6 times 0 is 0, minus 2/3 times 0 minus 1 cubed, plus 2 times 0, which is 0, minus 6 over pi, sine of pi over 2 times 0, which is 0. And then remember, you don't have to simplify anything. So I would leave it right there. Now, if you did simplify, you'd get 44 over 3, but it's a waste of time. And especially for those of us who maybe struggle a little bit more with our trigs than with some of our other evaluations, don't simplify. This problem, like I said, was worth 4 points. 1 point was for that initial setup, the integrand piece. Okay? 1 point was for the antiderivatives of specifically these first 3 terms, not including the cosine. So if you messed up on that u to u substitution, that's okay. If you got these 3 antiderivatives right, you got a point. The other point did come from that cosine antiderivative. So that's where you would lose a point if you forgot the u to u substitution, for example. And then 1 point came from your answer. If you made a mistake in your antiderivative, as long as you didn't oversimplify the problem, you still got your answer point as long as you plugged in correctly to your antiderivatives, whatever they happen to be. And then if you had written this all correctly but simplified wrong, most common mistake actually is not the trigs, believe it or not. The most common mistake with this problem was in plugging in the lower. There were a lot of people who are like, they're all going to be 0. I'm plugging in 0. But they aren't all 0. Look at what happens when I plug in 0 to this term. That's -2/3 times -1, which is a number. That's 2/3 here. When I plug in 0, I don't get 0, I get 2/3. Right? And so it's very tempting to want to make those kind of mistakes, so don't simplify. Write it out, leave it alone, call it good. Okay? Part B, I think, is, again, in my opinion, you might differ, but in my opinion is the most challenging of the 3, but it was only worth 2 points, so that's okay. A reminder that you will see challenging parts on your AP test. You need to prepare yourself for that fact. It is going to happen. I'm sorry. It is a reality. It happens every year. It's going to happen again this year. You might not finish an FRQ. You might hit a part that you're like, I don't know exactly how to answer this one. Well, give it your best shot. Don't leave it blank. Put down anything you can think of related to the problem. Take a derivative, take an integral, plug something in, do something, and then don't sweat it, right? You don't have to get all the problems answered to be able to get a 4, a 5, or a 3, right? You don't have to get 100%. That's not the goal. Skewed percentages, right? Okay, so part B, region R is the base of a solid. For the solid at each x, the cross section, so now we're talking 6.3 here, perpendicular to the x-axis, that's handy. That means I'm in terms of x. Has area of 1 over x plus 3. Well, what do you know? They've already plugged in a formula to my area. This isn't a square or a equilateral triangle or a semicircle. They've already given me the area. It's 1 over x plus 3, so I'm good to go. Now, a reminder that if they did say square, triangle, something like that, you would have to plug your upper minus lower into whatever that formula is. In this case, they've already done that. They've plugged the x plus 3 in. Okay? And so then integrating that, that is the natural log of the absolute value of x plus 3. Plugging in the upper is the natural log of 5, minus plugging in the lower, the natural log of 3. And then don't simplify. Okay, 2 points. One was for the integral, and one was for the answer. Okay. And last but not least, part C. This is the one that I view as the easiest, or the most straightforward, I should say. Everyone has different definitions of easy, right? But the most straightforward of the 3 parts, it's worth 3 points. Write, but do not evaluate, an integral expression that gives the volume of the solid generated when r is rotated. So we're talking that pi, big R squared, minus little r squared, d something. 6.2. Generated when r is rotated about the horizontal line, y equals 6. Well, y equals 6 would be up here. That's what I'm rotating around, y equals 6. Okay, that's the x-axis. So we're going to be in terms of x. Woohoo, I don't need to change my bounds at all. It's just 0 to 2. My big R, remember, is from the axis of revolution all the way across the shaded region. Little r is from the axis of revolution to the shaded region. And then whichever 2 functions you just connected. For big R, we connected 6 to g of x. And so big R is 6 and g of x. Little r connected 6 and h of x. And so little r is 6 and h of x. And then it said write but do not evaluate, so you're done. 1 point came from the limits and constant, which is that pi out front. You did have to have the pi there to earn that point. 1 point came from the form of the integrand with the big R squared minus the little r squared. And 1 point came from the integrand itself. So I'm just going to put plus 2 for these pieces here. And if you didn't get it all right and you're like, I don't know if I got 1 out of 2, send me an email. I'm more than happy to check that for you. Okay? Okay, next up we have, out of 2018, a non-calculator, slope field, and differential equation. Consider the differential equation dy dx equals 1/3 x times y minus 2 quantity squared. First up, we have a slope field for the given differential equation as shown below. Sketch the solution curve that passes through the point 0,2 and sketch the solution curve that passes through the point 1,0. Okay, so let's do 0,2 first. 0,2 is right here, and the solution curve that goes through that point is a line. Okay, and then 1,0 is here. This one, if I were to continue this up, kind of comes up like this, and it comes down, something like this, curves around, like so, comes up and over, and looks something like that. Okay? Okay, this one was worth 2 points. 1 for each curve, except they did have a couple of things that you had to make sure you did. First, you do need to make sure you actually go through the point that they say to go through, right? So, to earn this point, for example, at 0,2, you need to make sure you went through 0,2. Same thing with this one at 1,0. Second, you have to follow the given slope lines, meaning your curve needs to look somewhat like these. And you can see on the rubric that, for example, their U curve actually came down and was a little bit higher up. That's fine, that's okay, but you need to follow the general slope fields. And then the last thing that you need to make sure is that you extend it to the boundary of the slope field, which means you can't just like do a little U in here and not go all the way to the edge. You need to make sure you go all the way to the edge every time, right? All the way. Okay? Okay, part B. Part B, we have done quite a few of these as well. There was one in your FRQ 5, for example. They've been in quite a few of the FRQs. It's a very common question. It's also been in the multiple choice practice we did. Equation of the line tangent to the graph. Should Q for us, y minus y1, equals m times x minus x1. Okay, so let y equals be the particular solution to the given differential equation with the initial condition f of 1 equals 0. Write an equation for the line tangent, that, at x equals 1. Use your equation to approximate f of 0.7. Okay? Well, we're doing it at x equals 1, so let's go ahead and put that in first, at x equals 1. Okay? What's the y at x equals 1? Well, the y at x equals 1 is 0. And what's your slope? Well, slope, remember, is the same thing as derivative. And our derivative is this. I've said this several times, but I'm going to say it again. Make sure you don't put that equation into your slopes spot. That equation represents every possible slope. We want one particular one, the one at 1, 0. And so I'm not plugging that derivative in as its equation. I'm plugging that derivative in with the point 1, 0 plugged in. Now, you don't have to simplify this. You could take this entire piece and put that into the m spot and call it good. Or you could simplify this to be 4/3, whichever one you prefer. And then using your equation to approximate f of 0.7, plugging 0.7 into my equation, 4/3 times 0.7 minus 1, adding the 0 over, which doesn't really mean doing anything in this case. However, if this had been y minus 1, you would need to make sure you added that 1 over to the other side. And so for consistency's sake, I am going to show adding the 0 over to the other side, even though I recognize adding 0 doesn't do anything. Okay, and then you don't have to simplify. Leave it alone. There's really no reason to. If you did simplify, this would simplify down to -2/5 or -0.4, depending on if you prefer fractions or decimals. But again, I'd call it good. Okay? Okay, like I said, 2 points. 1 was for the equation of the line tangent, 1 was for the approximation. If you made an error with your equation of the line tangent, but you plugged 0.7 into your equation, you could still get your approximation point, even if you got this equation wrong, as long as you didn't oversimplify the problem. Okay? So again, let me know if you have questions on grading that. Okay? Find the particular solution y equals f of x to the given differential equation with the initial condition f of 1 equals 0. 5 points, the same 5 points that have pretty much always been there. We're now finding the particular solution. So dy dx equals 1/3 x times y minus 2 quantity squared. Okay? So, first point, separating the variables, dividing this y minus 2 squared over to the other side, and multiplying the dx to that side. And then I'm going to go ahead and rewrite this so I can use my power rule on it. We're now going to take the integral. Adding 1 to the exponent, dividing by the new exponent, we would have -1 over y minus 2, because that'd be y minus 2 to the -1. So drop that y minus 2 to the bottom. Over here, same thing, adding 1 to the exponent, dividing by the new exponent, we'd have 1/6 x squared. Okay, and you've earned 3 of your 5 possible points so far. 1 came from the separating variables, and 2 came from your antiderivatives. Last 2 points are the same 2 that they've always been, which is solving for c and solving for y. Okay, so plugging in my point to solve for c, we have -1 over 0 minus 2 equals 1/6 times 1 squared. Which is -1 over -2, which is 1/2, equals 1/6 plus c, and then subtracting the 1/6 over. Again, remember, you don't have to simplify anything, so you can call it 1/2 minus 1/6 if you'd like. I am going to go ahead and do that subtraction. 1/2 minus 1/6 is 1/3. But again, you can call it 1/6 minus, or 1/2 minus 1/6, that's fine. Call it -1 over 0 minus 2 minus 1/6 times 1 squared if you want to. You really don't have to simplify anything as long as you solve for c accurately. So that got you a point. And then plugging it back in and solving for y. Multiplying this y minus 2 over and dividing this stuff underneath the negative 1. It'll be here. And then adding the 2 over, you'd have 2 plus negative 1 over 1/6 x squared plus 1/3. Okay. Okay, again, if there are any questions, send them my way. I'm here to support you. Last one, we have our non-calculator out of 2017, particle motion. So two particles move along the x-axis, 0 to 8. The position of the particle P at time t is given by this position function. So, position, while the velocity of particle Q is given by that one. Particle Q has a position, x equals 5, t equals 0. So again, out of my experience, I always set up my desired position formula when I see that kind of given point, just in case I end up needing it. Okay? Okay, A, for 0 to 8, when is the particle P moving to the left? Okay? Well, particle P moves left when its velocity is negative. And so we're going to go ahead and find the velocity of particle P first off. Well, velocity of particle P is the derivative of its position. Okay, well, how do you take the derivative of a natural log? U prime over u, so u prime, 2t minus 2, over u, t squared minus 2t plus 10. And we want to figure out where that is negative, so we're going to go ahead and set this equal to 0. Okay, what would make this equal 0? Well, 2t minus 2 would need to equal 0 for that to equal 0. And so t then would equal 1. If I did my little number line test, plugging 0 into my velocity, I get a negative over a positive, which is a negative. And when I plug 2 into my velocity, I get a positive over a positive, which is a positive. And so my particle is moving left less than 1, which is everywhere from 0, where I started, to 1. Okay, this one was worth 2 points. Whoops, dropped my pen 1 second. Okay, this one was worth 2 points. 1 point for taking the derivative of velocity, and 1 point for your answer. Okay, B, for what time intervals do the two particles travel the same distance? Sorry, not same distance, same direction. Well, we know what direction particle P is moving. It's moving left from 0 to 1 and right from 1 to 8. So really the question is, where is particle Q moving? What direction? And then to compare those intervals, okay? So we would have our velocity of Q that we would need to use, which was our t squared minus 8t plus 15. And we're going to set that equal to 0. Okay, this factors to t minus 3, t minus 5, which gives me two values, 3 and 5, that I can put on my number line. Okay, testing those, when I plug in 0, I get a negative times a negative, which is a positive. Plugging in 4, I get a positive times a negative, which is a negative. When I plug in 6, I get a positive times a positive, which is a positive. Okay, so now I know how particle Q is moving. And so if I compare the two of them, right, this is particle Q and particle P. I'm going to go ahead and put their number line underneath. One would be like way over here, negative, positive. If I were to try to kind of make it line up with their number line here. Okay, well, your particle P is moving left from 0 to 1, particle Q is moving right from 0 to 1, so that's not an interval, right? But starting at 1, particle P is moving right. So everywhere from 1 to 3, particle P is moving right, and particle Q is moving right. But starting at 3, particle Q, between 3 and 5, now moves left. Particle P is still moving right, so they're not moving the same direction there. However, starting again at 5, Q now moves right again, P is still moving right, so 5 to 8. You'd be moving right together again. Okay? And you get 2 points for this. 1 point for your answer, and then 1 point for your analysis of the two. Okay? Looks like in the rubric they included an explanation, so I'll go ahead and jot down my version of an explanation because V sub P of T and V sub Q of T are both positive on 1 to 3 and 5 to 8. That would be my explanation if I was asked to give an explanation. Okay. Okay, C, we have find the acceleration of the particle Q at time t equals 2, and then is the speed of particle Q increasing or decreasing, or neither at time t equals 2. Explain your reasoning. Okay, so first up, let's go ahead and find the acceleration of Q. Okay, the acceleration of Q is the derivative of its velocity. Okay, well the velocity of Q is this function, so its derivative would be 2t minus 8. And so the acceleration at 2 would be the derivative of velocity at 2, which is 2 times 2 minus 8, or negative 4. And so then their question then becomes, is the speed of the particle increasing, decreasing, or neither at t equals 2? Explain your reasoning. And so what does it take for speed to increase, decrease, or neither? Okay, well this is on the back side of the first page of your particle motion packet. Speed is increasing when velocity and acceleration have the same sign, and is decreasing when they have different signs. Well, I know that my acceleration is negative, so the question then becomes, what's my velocity at that point? Because if it's also negative, then my speed is increasing, but if that velocity is positive, then my speed is decreasing. What would it mean for my speed to be neither? It would mean something would be 0. Right? 0 is neither positive nor negative, and so it can't have the same sign or different signs than any other value. Right? Okay, so let's go ahead and find velocity at 2. Again, that's my velocity function, so I'm plugging 2 in. Which is 4 minus 16, which is negative 12, plus 15, which is 3. And so because that's negative and that's positive, my speed is decreasing. At t equals 2. Oops. Because a sub q of 2 is negative, but v sub q of 2 is positive. So therefore they have different signs. And again, there's not one right explanation, so if you explained it a different way, I'm more than happy to check if you explained it correctly or if your explanation would work, but that's mine. Okay? 2 points. 1 point came for finding the acceleration at 2, that negative 4, and then 1 point came from your answer of decreasing with a reason. You did have to have a reason. Okay, part D is worth 3 points. Find the position of the particle Q the first time the particle changes direction. Okay, and so we're finding a position function here for Q. At the first time it changes direction, well, we know where Q changes direction because we know Q's movements. We found it up here in part B. Q is moving right to 3, left to 5, and then right after that, the first time it changed direction was at 3. And so we're finding the position at 3. Okay, well, our desired position formula, we jotted it down up here, is 5 plus the integral from 0 to t of our velocity. So 5 plus the integral from 0 to 3 of our velocity. Okay, which is 5 plus antiderivative of t squared is 1/3 t cubed, 4t squared, and 15t. Plugging in the upper, we'd have 3 cubed 1/3, which is 9, minus 9 times 4, which is 36, plus 45, and then it would be minus 0, 0, 0, so I'm not going to write that. Again, you don't have to simplify. But if you did, that would simplify down to 23. Okay, 3 points. 1 came for the antiderivative, so taking the integral there. 1 point came from using your initial condition, the plus 5, and 1 came from your answer, with, again, the potential for partial credit if you made an error, depending on if you oversimplified the problem. Which again, if you're not sure, I don't know if this oversimplifies, like did leaving this off oversimplify it? I'm more than happy to check that for you. Okay? Okay, let me know if you have any questions.